Let's finish up with another problem that's somewhat similar. This is number 35. It says two manned satellites approach each other at a relative speed of 0.250 meters per second intending to dock, which means they're approaching each other at in opposite directions if they're both moving. And the total of their speed, if you're sitting in one or the other, is relative 0.25. The mass of the first one, this is number 35, the mass of the first one is 4 times 10 to the third kilos, 4,000 kilos. There's 0, 0 here. And the mass of the second one is 7.50 times 10 to the third, so 7,500 kilos. And it says to calculate the final velocity after docking by using a frame of reference in which the first satellite was originally at rest. So V1 is 0, and V2 is therefore going to be the entire velocity of 0.25. And you can say that that's minus, and then it's going right to left. Say this is M1. It's not moving actually, so let me get rid of that arrow. M1's not moving, but M2 then is traveling in this direction, and they're going to dock, so ultimately they're going to be stuck together. And it says, what is the final velocity? So again, M1 V1 plus M2 V2 has got to equal the docked mass together times the new velocity. This is 0 because M1 is 0, or V1 is 0. So you have 7.5 times 10 to the third times 0.25 has to equal the sum of these two, which is 1.15 times 10 to the fourth. 7.5 plus 4 is 1.15, and increase by one number there, times v, the new velocity. And this is a negative because I said it was moving from right to left. And v then is going to be this divided by this larger number. And if you do that calculation, you get a minus 0.163 meters per second, minus, which means it's going to move from right to left. Now B says, what is the loss in kinetic energy in this inelastic collision? Okay, so this is not moving, so we don't have to worry about this guy. So this is the initial kinetic energy, 1/2 times 7.5 times 10 to the third times 0.25 squared. And that kinetic energy is going to be 234 joules. And then after the collision, you got 1/2 times the new mass, 1.15 times 10 to the fourth, times 0.160, or 3, negative, squared. But the negative doesn't matter because we're going to square it. And that's going to be 193. If you subtract these two from each other, 153. And if you subtract these two from each other, you lose 81 joules. You start out with this many joules and you end up with this many joules, so you lose 81 joules. Now it says repeat both parts, but reverse the frame of reference. That is, you have the second V2 is now 0, and so now V1 is 0.25, and we're going to say it's positive, and V2 is 0. So in this top equation, we're going to end up with, I'm just going to write this down, 4 times 10 to the third times 0.25. That's going to be, instead of this being canceled out, this is canceled out. So you have 4 times the velocity. And that's going to equal this 1.15 times 10 to the 4th times the new v. And the new v now is not going to be, it's now going to be 0.087 meters per second. Now it wants you to calculate again the loss in kinetic energy. So you have 1/2 times 4 times 10 to the 3rd times 0.25 squared. And that's going to give you a kinetic energy of 125 joules. And in the second one, it's this one is going to be 1/2 times 1.15 times 10 to the 4th times 0.087 squared, and that's going to equal 44 joules. And lo and behold, if you subtract these two, you get 81 joules lost. So the loss of energy, when you reverse the frame of reference, is exactly the same. And the question is, why is that? And the reason that is the fact that regardless of the frame of reference, the loss is going to be in the same, for the same reason. And so the loss is going to be the same regardless of which frame of reference you use. Primarily because there's no other point that's made in the problem to suggest that there's a change in where the loss would go. The next problem is problem number 36. Says a 30,000 kilogram freight car. So let's call that 30,000 kilograms. That's 3.0 times 10 to the 4th kilograms. Is coasting along, that's M1, is coasting along at 0.85 meters per second. And there's negligible, now it comes under a hopper and suddenly we dump 1.1 times 10 to the 5th kilograms of whatever scrap metal into it. What is the final velocity of the loaded car? Well, this is an interesting problem because instead of collision, what you basically are doing is changing the mass without changing the potential energy. So you have potential energy with this mass and the potential energy with the additional mass, and these have to be the same. So this has to slow down so that M1 V1 has to equal M2 V2, where M2 represents the sum of this and this. So M1 V1 has to equal the new mass, which is going to be 1.4 times 10 to the 5th times v. If you do the math here, you end up with a velocity of 0.2 meters per second. Now it's asking, again, it asks, what's the loss in kinetic energy? Well, the first one, you have 1/2 mv squared. So it's going to be 1/2 m1 v1 squared. That's going to be 1/2 times 3 times 10 to the 4th times 0.85 squared. And that's going to equal 11,000 joules. And the second one, you'll have 1/2 times the new mass, 1.4 times 10 to the 5th, times 0.2 squared. And that's now going to be 2,800 joules. So you, in the process, you lose 8,200 joules. 8,200 joules are lost when you dump that metal in there. Number 41. Number 41 states the following. 2 football players collide head-on in midair while trying to catch a thrown ball. The first player is 95 kilos and has a velocity of 6. The second has 115 and has a velocity of minus 0.35. What is their velocity after impact if they cling together? Now this is actually quite simple, and we've done several of these already. You have 95 times 6 plus 110, or 115, excuse me, 115 times minus 3.5 divided by their sum of their weights, which is going to be 210 kilos, is going to equal their new velocity. And their new velocity is going to be 0.798 meters per second. And it's positive. You can see that it came out positive. So that means that it's going to be in the direction of this football player from left to right. 46. Now 46 is the hardest problem we do today because it's in 2 dimensions instead of 1. And when you start talking about momentum in 2 directions, actually 48 is the hardest one mathematically. When you talk about 2 dimensions, you have to start talking about momentum in terms of its x and y component, just like when we talked about velocity vectors, x and y component, and force vectors, x and y component. So C just wants you to prove, it says confirm that the results of the example 8.7 do conserve momentum in both the x and the y. Well, if you write down, you have mass 1, which is traveling at 2 meters per second in this direction, and mass 2, which is not moving. So V2 is 0, and V1 is 2. And the mass of mass 1 is 0.250 kilograms. And the mass of mass mass 2 is 0.40 kilograms. And they did and showed that after the collision, you had 45-degree angle here, and what they call 312-degree angle, which is a minus 48-degree angle here. And this was M1 down here and M2 up here. Now, they called it 312, which is the same as a minus 48 degrees. You start here, 45 degrees, you go all the way around. I should write it on this time. 312 degrees would be over here. So basically, what you want to prove is that the x and y components are conserved. So if the x component, this is traveling horizontally. So the x component is entirely from that ball, and its entire momentum is in the x component. So all of that has to now equal the 2x components of this. And one would be the same mass. So we're looking at this one down here now. Its new velocity, which was given in the example, is 1.50, and now it's going to be cosine of 45 degrees. That's the x component of this momentum, plus 0.40, excuse me, times its velocity, which is given in the example problem as 886, times the cosine Now you can either put minus 48 or 312. And if you do that, this is 0.5, and this is going to be 0.265, and this is going to be 0.231. If you add these two together, you get 0.496, which is close enough for rounding. Now, there was no y component. When you do the y component, the initial had no y component. The x component, or the y component, is going to be 0.250 times 1.5 times the sine of 45 plus 0.4 times 0.886 times the sine of 312. And if you add, this is a negative number, and they cancel each other out within the rounding error. Now briefly, I'm not going to go through the whole math of this, but let me briefly show you number 48. Number 48 says that you have a bowling ball that has a mass of 5.50 kilograms, and it's going at 9 meters per second, and it strikes a pin which has a mass of 0.850 kilograms, and the velocity of the pin is not known. And when the pin is scattered at an angle of 85 degrees of the initial direction of the ball, so the pin, here's the ball direction, the pin is going to go like this, 85 degrees, and the ball is going to go like this, and you don't know this. Okay, so you have two unknowns, so you have to use that. You have two unknowns and you have to have two equations to calculate two unknowns. The two equations come from the x component and the y component. The x component, you start out, the x component comes from the bowling ball, 5.5 times 9 has got to equal 5.5 times some number that you don't know, v1 prime, times the cosine of this angle you don't know. In other words, it's got to go off, it's going to go off in a new velocity here and a new angle, neither of which you know. So the x component is going to be equal to this plus the mass of the pin times its velocity, which is 15. I didn't write that down. I should have written that down. Actually, that goes right here. Well, its initial velocity is 0, and its final velocity given in the problem is 15. And then its angle is 85 degrees, so the x component of that is the cosine of 85 degrees. So that's your first equation. And the second equation is the y component, which is going to be 0 because there was no y component. 5.5 times v1 prime times the sine of theta plus 0.850 times 15 times the sine of 85. And if you work these down, you end up with v1 prime cosine theta is equal to 8.798, so that v1 prime is equal to 8.798 divided by the cosine of theta. So that's just simplifying this. And if you work this down, you end up with V1 prime times the sine of theta is equal to minus 2.309. Okay, so you can substitute for one of these two. You can put this in for this, and so you can change this around and say V1 prime is equal to minus 2.309 over the sine of theta. So let's put this in up here. So you have minus 2.309 sine theta is equal to 8.798 for the cosine of theta. And that ends up being 8.798 sine theta over cosine theta is equal to minus 2.309. Now, this is an identity in trigonometry. It is the tangent of theta. So the tangent of theta becomes this number divided by this, which is minus 2.26, no point. It's 0.2624. So theta is equal to minus 14.7. So this is minus 14.7. Or you could write it down as 360 minus 14.7, which is about 355 or 345. And if you substitute this in over one of these equations, you end up with V1 prime is going to equal 9.1. Now, interestingly, if you calculate the kinetic energy of these, now kinetic energy doesn't have a direction, okay? So basically what you write in is 1/2 mv squared, and the initial is 1/2 times 5.5 times 9 squared. And so the initial kinetic energy is 222.75. The final is 1/2 times 0.85 times 15 squared plus 1/2 times 5.5 times 9.1 squared. If you add those together, you get 95.63 plus 228. So you end up with more kinetic energy after the collision. Now, how does that happen? Well, basically, they speculate that spin on the ball or something else has caused this to happen. But this can happen if there's some sort of energy that's imparted for reasons other than the linear movement of the ball. The last problem is problem number 52, which I'll go through very quickly. M1 is equal to 90 kilograms. Let me read 52 very quickly for you. It says, a 90 kilogram hockey player hits a 1.15 puck, giving it a velocity of 45. If both are initially at rest and the ice is frictionless, how far does the player recoil in the time it takes the puck to reach 15 meters away? So M1 and V1 is 0. M2 is equal to 0.5 0.150, and then afterward, and V2 is equal to 0. So that means that there's no kinetic energy until after the two objects are struck, or this object struck. So V2 prime is 45 meters per second, and they want to know what V1 prime is. And, well, you have to calculate what V1 prime is in order to calculate the distance. So 90 times V1 prime has to equal 0.15 times V2 prime, 45. So V1 prime equals 0.075 meters per second. And the distance is equal to the velocity times the time. And so the time here, distance over velocity, which is going to equal 15 meters divided by 45 meters per second, so 0.333 seconds. And then if you multiply that by this new velocity, you get 0.025 meters. And that's the distance he travels.